The next type of bonding we're going to talk about in our unit is covalent bonding. Covalent bonding can also be referred to as a molecular compound, or we could say molecular compounds have covalent bonds, or covalent bonds make up molecular compounds. The two words are interchangeable in terms of what type of bond they have. So a covalent bond is different from an ionic bond because in a covalent bond, we're sharing electrons. Right? And it's a sharing between only nonmetals. So there's a big difference between how electrons are shared and between what types of atoms the electrons get shared by. So we're going to be talking about sharing, and as many of you have probably heard in your past, sharing is caring. And we're going to see how that relates to bonds and chemicals now. Later on in the next video, we're going to talk about what the difference of a polar covalent and a non-polar covalent bond are. But for the sake of today, we're really just going to be talking about the overarching covalent bond. If you're taking higher levels of chemistry, it's important to note that the electronegativity difference would have to be less than 2. This is something that would classify a covalent bond as a covalent bond. Example, H and O bonds from an H2O molecule. A 2.2 electronegativity, a 3.4 electronegativity. The difference here is 1.2. The END is 1.2. This number, the difference between hydrogen and oxygen, would let a higher level of chemistry student know that it's a covalent bond. So covalent bonds can show up in 3 different ways. We could show them up as single bonds, we could show them up as double bonds, we can show them as triple bonds. And that basically just means 2 electrons being shared between 2 atoms, or 1 pair of electrons, or 2 total electrons. This is the bond. These 2 electrons dance back and forth between the hydrogens, creating a single bond. I think the best way to explain what sharing looks like is for me to show it in a different way. So, in a very simplified way, a sharing of electrons between 2 hydrogen atoms starts out with, your 2 dots, your 2 electrons in the middle. But very different from an ionic bond, where the electron just gets moved from one atom to the next. These electrons bounce back and forth, and they almost create this type of, we'll call it a figure 8. Like I said, this is a very simplified version. And they just kind of go back and forth, and they keep the 2 nuclei bound together because they can't basically decide where they want to end up. And this interaction of 2 electrons going back and forth is what a covalent bond really is. So if we bring this into the concept of a double bond, it's the same idea, but instead of 1 single pair of electrons being shared, we denote 2 pairs of electrons shared. Each pair is represented by, like this line is equal to 1 pair. Right? So if I have 2 lines, I have 2 pairs. If I have 3 lines, I have 3 pairs. Now all this means is that not only are we dealing with one pair of electrons dancing back and forth between the 2, we're dealing with a whole second set of electrons at the same exact time, also bouncing back and forth. A double bond is stronger than a single bond, right? Because you have more electrons keeping these atoms together. And a triple bond is, like in nitrogen, is 3 valence electrons, or 3 pairs of electrons shared between the 2 atoms. And yes, you guessed it. We've got 3 sets of electrons bouncing back bouncing back and forth. Let's just move that over there. Get that out of the way. 3 sets of electrons bouncing back and forth to create a bond between 2 atoms. This is a triple bond. Triple bonds are stronger than double bonds. Double bonds are stronger than triple bonds. The electrons just bounce back and forth between the 2 atoms to hold them together. You know, I just want to remind you that when we did ionic bonds, we literally take the electron and transfer it somewhere else. So the attraction here comes from the positive and the negative. There's no movement of electrons in an ionic bond between the atoms. The movement from a covalent bond happens as you've seen here. Some important Lewis dot diagrams that you want to be familiar with are H2. Now, this is how it works. So you have one hydrogen and you have a second hydrogen. Those 2 hydrogens each have 1 valence electron. Ideally, they want 2. But neither is strong enough to pull the electron away from the other. So instead of the electron moving and leaving one atom and joining another, they work together by creating that figure 8 effect around both atoms, and they create one bond. In oxygen, I like to say to my students, some of them are you, but I like to say, when you put your valence electrons for your dot diagram on, you want to go around a compass or around a clock. You know, north, east, south, west, north, east. And if I did that for 2 separate oxygen atoms, north, east, south, west, north, east, what we're going to see is some lone pairs of electrons, right? And some unpaired electrons. On the north side of both of these atoms, we're going to see a pair of electrons. These 2 electrons don't bond. They don't like to bond. They are paired. They don't like to bond. The ones on the east side of both are also paired. They don't like to bond. Once an electron is paired, it won't bond. But the south side, right, and the south side, and the west side and the west side, they're not bonded. So what they do is they interact with one another and create a pair. Now the oxygen doesn't realize it doesn't necessarily have the electron, but it has it some of the time. It shares it with the other oxygen, creating a double bonded covalent bond between the 2 O's in oxygen, and it looks like that. For water, water is a big one that people kind of make a mistake about. Again, I will go north, east, south, west, north, east. And I'll even draw the hydrogens both here and both here. So to remind you, the north side is paired and the east side is paired. So we're just going to ignore those for bonding purposes. What we notice is that the west side needs a pair and the hydrogen needs a pair. So we act as a matchmaker and we're going to match those up. The south side needs a pair. The north side of hydrogen needs a pair, and we're going to pair those up too. Now it's really important to realize that those bonds on that oxygen took place on the south side and they took place on the west side. And that's why our water molecule, when we draw the proper Lewis dot diagram, has this angle, this 90-degree-ish looking angle to it. It's called a bent shape. But for the regions, you don't need to know that. But you do need to know that water molecules look like that. They don't look like a linear straight line. And these last couple of ones, I'll just kind of put them on the board for you to see. they are some other very common diagrams that come up in any chemistry class. That would be CH4, carbon dioxide, looking like that, and NH3, looking like that. If you are somebody who takes the New York State chemistry regents, I would say these 6 molecules are ones that you really should know and ones that you should practice drawing because they do frequently show up. So I hope you enjoyed that video, and thank you for watching, and stay tuned for the next one.